Hey guys. So today we are going to be looking at volumes of revolution with the Washer method again, but looking at constants, right? So like x equals a constant or y equals a constant as our axis of revolution. And we're going to be doing a few regions, well, one region that we also looked at in yesterday's video, but revolving it around a different axis this time. So if you have the notes from yesterday handy, that might be nice if you just want to kind of compare at the end, but you don't have to. And yeah, let's dive in. All right. So to kind of summarize what we were looking at yesterday, um, with the washer method, so we have two radii now, right? Big R squared minus little r squared. And yesterday we were looking at revolving those regions with the outer radius and the inner radius around the x-axis and the y-axis. So we're going to look at constants today like y equals 1 or x equals 1 as opposed to just y equals 0, x equals 0. But all that really is going to do is it's just going to change how we calculate, excuse me, the big R and the little r, right? So that we're going to have some constant that we're going to have to subtract as we consider our top minus bottom for dx or our right minus left for dy. Um, so like with axes, like the x-axis or the y-axis, it's just 0, so you don't really have to think about it, right? But if you're revolving around like y equals 1, 1 might be the bottom or it might be the top, so it factors into how you're calculating both radii, right? Both the big R and the little r, because it's going to affect what that radius looks like. And that's going to make more sense when we actually look at some graphs. So let's do that. Okay, now this says if the same region is rotated about the line x equals 2. This is referring to an example we did yesterday where we've got y equals 2x and y equals x squared. And yesterday we took that region and we rotated that around the y-axis. Well, today instead, we're going to be rotating it around the line x equals 2. Now, as always when we're doing volumes of revolution, you want to pay attention to the axis first because it tells us two things. It tells us what type of shape it is. Is it a disc or a washer? And it's going to tell us what variable we're working with. Horizontal axis would be dx, vertical axis will be dy. So x equals 2 is a vertical line. Unfortunately, that means this is going to be a dy scenario. Womp womp. Also, x equals 2 is neither of the curves bounding my region, right? I've got x squared at 2x, and neither of those are x equals 2. So that tells me that this is going to be a washer. Okay, but we're not revolving around the y-axis like we did yesterday, right? We're revolving around x equals 2. And that actually creates a different shape, which is interesting. So it's changed around what my radii are going to be in this scenario. Because yesterday our outer radius came from the parabola and our inner radius came from the line, but now that's no longer the case. When you're determining which is the outer and which is the inner radius, it's about which one's farther away from the axis. And if my axis is over here, if I'm revolving around x equals 2, then my farther out radius is coming from the line and my smaller radius is now coming from the curve. So those are switching around. All right. So first of all, it's still vertical, right? That we've still got stuff in terms of y. We looked at this yesterday, right? Divide by the 2, take the square root. Okay, so I've got my big R and my little r, again, being determined by what's farther away from the axis. The one that's farther away, which in this case is that line, is going to be formed the outside of the shape. So this shape is kind of pointy on the outside, but then it's going to be curved from the parabola on the inside. So it's different. And again, revolving around this x equals 2 over here. Okay, so the outer radius. Now, because I'm doing a dy, that means I'm having to think right minus left for that radius. So the right is the axis itself, so it's 2. right? That is my right is 2. And then the left is coming from the line, which switched around for y, is y over 2. So that outer radius is right minus left. The inner radius will also be right minus left, but it's a different right minus left. Yeah, right minus left. There we go. The inner radius is also 2 minus, but the left now for little r is coming from the curve, so it is root y. So right minus left is 2 minus root y. Our boundaries are the same as yesterday. They're 0 to 4, and that's because these two curves still have the same points of intersection, right? At y equals 0 on the bottom, y equals 4 on the top. We're just spinning it around a different axis, but that hasn't changed what the region itself, the 2D part of this, it hasn't changed what that looks like, so we still have the same boundaries. All right, we're ready to put it all together in an integral. Boom. Now, remember, just like we were saying, kind of in a general sense first, right? We've got pi, you've got your bottom to top for our dy, and then big R squared minus little r squared dy. So here it all is. Isn't that complicated? Hooray. So we've got pi, the definite integral from 0 to 4, and then we've got big R squared, which is a right minus left, minus little r squared, which is also a right minus left. Same right boundary for both because they're both revolving around the same axis. And then dy. And remember, all of this is coming back to cylinders, right? Pi r squared h, just good old calculus coming along and making it more complicated, right? Because r is not the same, r is varying. So that's why we need calculus, because calculus is the mathematics of change. Anyway, I'm going to very quickly click through all the arithmetic here because it's, you know, awful. It's a lot of algebra, and this is not AP algebra, right? So just to show you that it can be done by hand, eventually, again, this is something where I'm much more interested in making sure that you know how to set it up, right? Not doing all that solving by hand because that's very algebra intensive, and that's not the intention of the AP exam, and it's not the intention of this course. Eventually, you get 8 pi over 3. Now, I want to point out, if you compare this to the one we did with the same region and a different axis yesterday, it is this time the same. We did the y-axis yesterday with the same region, and we also got 8 pi over 3. This one, there is symmetry in such a way that that happens for both of these axes. However, if I were revolving around like x equals 4 over here, I'm going to kind of go a little wild with the highlighting here for a second, but what would happen? So my radii would be huge, right? And you have to figure, okay, if I extended those radii in the opposite direction, I would have this very, very large hollow figure, right? That this would be spinning around and making this very big shape. So the distance to the radius, the axis of revolution, very, very much matters. Erase all of that nonsense. It very much matters, okay? Because what that does is it makes your radii much, much bigger, and that would cause your volume to come out much, much bigger, okay? It just so happened that the way this balanced out at x equals 0 and at x equals 2, that they gave you the same volume, okay? Because it just balanced out. But it can be different depending on the axis, so don't assume that everything with the same base region is the same, because it's very much not. All right, so we are going to do kind of a three-parter with this one. So we're going to consider the region S enclosed by the graphs of y equals 4 minus x squared and y equals x plus 2. We're going to do area, and then we're going to do a couple different washers with this region. Area is pretty much it just goes hand in hand with volume, right? So we're kind of circling back to that. So don't forget, area, right, is just top minus bottom, or right minus left, and without the squares and the pies and all that other stuff that we've introduced later. Okay, so if we want to find the area of this region that's enclosed by these graphs, we need a couple things, right? From the graph, we can see what the top minus bottom is going to be, but we also need points of intersection. Now, I did this in Desmos, and I didn't turn off the graph line, so you can kind of see what the points of intersection are. But it is important to remember, yeah, so we've got the curve on top, obviously, and the line on the bottom. But it's important to remember that to find points of intersection, to find those boundaries, algebraically, you're just setting those two curves equal to each other, right? That tells you when they are the same, and that's where they will have intersections. So we just do a little algebra. It's a quadratic. You want to set a quadratic equal to 0. You want to factor a quadratic. That's why we've done all these things in the past. It's all coming together. And then eventually we get -2 and +1, and those are our boundaries. Okay, so that's going to be our left and right. Those are going to be the bounds on our integral. Now for area, all you got to do is just do the integral from left to right of top minus bottom, and that's it. So just don't overcomplicate it. Not everything is squared. It just feels that way because we've been doing volume for a few weeks now, right? And volume adds another dimension, but area is just flat, right? It's a two-dimensional space. So it's just top minus bottom and integrate it, and that makes it two-dimensional. Okay, so this one says actually find the area, and it's not too awful to just distribute that negative and combine like terms, right? So there's a -x², there's a -x, and then it was 4 minus 2, so that's +2. And then we can just do our antiderivative. Cool. So we do the power rule. Powers go up by 1. Don't forget the +2 gains in x because the power goes up because we are integrating, not deriving. This does not have any symmetry we can take advantage of to get rid of like the lower bound and turn it into a 0. Like it's just not a symmetrical region, unfortunately. I can't like neatly cut this in half at the axis or anything like that. So you got to plug in the 1, you got to plug in the -2, you got to be careful with all the negatives, but eventually you keep going and it comes out to be 9/2. All right, so that's the area of the region. Don't overcomplicate it. It's not squared. Area is just top minus bottom. It's very easy to just think you want to throw in a pi or a square just because you get so used to it after doing a bunch of volume stuff, but no, don't overthink it. All right, so same problem stem, but we're going to do a part B of an FRQ now. Write, but do not evaluate. Oh, man, if those words are not music to your ears at this point, then you've not been paying attention. Write, but do not evaluate an integral. It means you don't have to solve it. How nice. That it represents the volume of the solid generated by revolving S. S is the region enclosed by these, right? Consider the region S. Okay, so we're revolving S about the x-axis. Okay, so volume, solid, generated by revolving. All right, cool. So as soon as you see the word volume and revolving, and I just want to point out, this is not if you see volume by cross sections, right? That's still fair game too, y'all. We've got all that cross section stuff from before, and we also now have revolution. So with all of those methods though, for cross sections, right, just like you would focus on what you were perpendicular to, with volumes of revolution, you are focusing on what are you revolving around, what's your axis. So we're doing the x-axis this time. Oh, that's great. The x-axis is great because it means we're dx. It also means this is a washer, but that our bottom function, right, if it's the x-axis, our bottom function is y equals 0. So that's really great. That's pleasant. Okay. So we need to determine, because we already determined our bounds on part A are at -2 and at +1, so that's cool. All we need to figure out is big R and little r. So we're revolving around the x-axis, which as I just said a moment ago, is y equals 0. All right. So draw in some radii, right? That you've got your region. It's not colored on this screen for some reason, but we've got our region here, right? So big R is whichever one is farther away, which is the curve, from the axis, right? So that gives you big R. So big R here is going to be 4 minus x squared minus 0, right? Because the bottom is y equals 0. Oh, man, so great. Don't we love the x-axis? It's the best. Little r comes from the other curve, okay? So that would be this x plus 2 minus 0. Okay, and if you want to kind of visualize, I'm going to attempt to sketch this on my surface, and we're just going to see how well this goes. Probably not great, right? But if you're revolving around this axis here, right, that you're making this big curvy thing, this is a really weird shape. It's super asymmetrical, right? But you've got this kind of like and then it's cut out kind of like this. Oh man, it's kind of like a 3D Pac-Man actually, except it goes all the way around, right? That it closes in, right? It closes in. It's kind of like a weird cutout eye almost. Anyway, that's unsettling. Um, but we've got our radii and we've got our boundaries. So now we're ready to set it up. Pi r squared minus r squared h. Boom. All right. Pi, integral from -2 to 1, right? So that's still left to right. And then big R, which is the parabola, squared, minus little r, squared, dx. That's it. Because it says write but do not evaluate. See? Best words ever. One more, based on the same premise, similar but not the same. Write but do not evaluate. Oh, an integral expression that represents the volume of the solid generated by revolving S about the line y equals 4. Okay, so we're still doing a volume of revolution, but now we're going around y equals 4. Y equals 4 is another horizontal line. Yay, it's another dx. And y equals 4 is not one of the boundaries, so it is another washer. It's just a different washer from before. And it's marked here on the graph, that dashed line, that's y equals 4. So that's going to be our axis of revolution this time. It's going to form a totally different shape. Okay, we need to determine our radii. Okay, now, again, sketching, see what I'm doing? I'm sketching in those little radii. Well, the big one and the little one, I suppose. So you're just drawing lines, right? Those represent the radius of the thing that you are spinning around. So big R goes to whichever one is farther away. Now notice this time, this one's a little bit different because that top minus bottom, the 4 is going to be the top for both radii this time because it is greater than both of these graphs because it's higher up. So for big R, it's going to be 4 minus the line x plus 2 because it's farther away. So it creates a larger radius. So that's big R. Little r is also top minus bottom, right? And it's 4 minus the curve. Now, can you simplify those? Yeah, sure, right? You could take big R and say, okay, it's 4 minus x minus 2. Okay, so it's 2 minus x, right? And with little r, you could say, okay, it's 4 minus 4 plus x squared. Cool, it's just x squared. Yes, you can simplify that. You don't need to, and I don't really recommend it. Honestly, oh no, my animation disappeared. I don't know what just happened. PowerPoint's been a little glitchy, so I'm just going to write it in. I could not get this glitch to go away when I was animating this slide, but we're going to just do what we can here. Okay, so pi integral from -2 to 1 of 4 minus x plus 2 squared. There's my big R squared minus 4 minus 4 minus x squared. squared dx. So, yeah, you can simplify your big R and your little r, but honestly, I wouldn't. Especially on a problem like this where it just says the magic words write but do not evaluate. Don't simplify. Because if you simplify and something like a negative sign messes you up, then just womp womp, right? You lose points that you would have otherwise earned, and that's painful. And even though this stuff is not on the 2020 exam, like this particular stuff is not there, I just think that's a good rule of thumb in general, right? If you don't have to simplify something, please don't do it. I know I've said that a bajillion times this year, but it's just it's a hard habit to break. Um, but if you don't have to simplify something, then don't. So I'm not simplifying this. We're done. Right? We wrote the integral. That's it. It's an integral expression that represents the volume of the solid generated by revolving the region about the line y equals 4. Okay, so guess what? Actually, can I turn my camera back on? Oh no, it won't let me do it in the middle of a slide. Guess what, guys? We just finished all of the AP Calc AB curriculum. That's it! Yay! We did it! We had to do it online, but we did it! That is the last new thing in the entire course. Yay! We have covered everything that universities consider to be Calculus 1. We've done it. So, pat yourself on the back. You made it. We're here. We're not physically here, but we're here. Yay! In our homes. Probably in our pajamas. I'm not in my pajamas. I'm actually dressed, but anyway. Thank you so much for watching, and I hope you guys have a good one. And bye.